Hello and welcome. My name is Glenn Abille, and this is my final project presentation for CSCI E116, Dynamic Modeling and Forecasting in Big Data with Professor William Yu. This project is about time series forecasting of wildlife strikes in United States civil aviation. My objective is simply to forecast monthly wildlife strike incidents using historical data from the FAA Wildlife Strike Database. The goal is to uncover seasonality, long-term patterns, and generate reliable predictions to inform proactive aviation safety planning. Now, why is this important to me? Well, wildlife strikes, including bird strikes, pose significant threats in aviation. Beyond the substantial financial burdens, which is estimated to be over 1.2 billion globally in repair costs, these events represent a critical safety hazard that can lead to catastrophic outcomes and the loss of human lives. As an example, the tragic crash of Jeju Air Flight 2216 in December 2024, where 179 fatalities occurred following a suspected bird strike during landing. This serves as a stark reminder of the potential severity of wildlife encounters for even large commercial aircrafts. Understanding the temporal dynamics of wildlife strikes is therefore essential not only for mitigating financial impacts, but more importantly, for enhancing safety. Analyzing strike patterns enables airports to optimize resource allocation for wildlife management, deploy deterrents for more effective based on seasonal variations in daily activity, and budget appropriately for mitigation strategies. Accurate forecasting supports data-driven decision-making and ultimately improves the overall effectiveness of wildlife mitigation strategies, helping to prevent accidents and protect the lives of passengers and the crew. Now, the dataset utilized in this analysis was obtained from the FAA National Wildlife Strike Database, a comprehensive public repository that documents wildlife aircraft collisions across the United States. Each record includes the incident date, location, aircraft speed and altitude, weather conditions, time of day, and wildlife characteristics. For this project, the analyses focused exclusively on incidents that occurred within the state of California. This project will serve as an example for other trade studies across the United States. The dataset was filtered accordingly, and relevant variables were extracted to support the time series modeling of monthly wildlife strike counts. A few processing steps were performed, and those are data import and filtering, variable selection through correlation analyses, handling missing data, data type conversion, and finally validating checks. On the right is a heat map of the strikes. These are at least two major areas of strikes, which are Los Angeles and San Francisco, which represents the busiest airport in California and perhaps in the world. Other areas are Sacramento, Fresno, and San Diego. They are all bird strikes within the state of California. A number of EDAs were performed for this project. The two presented here are monthly strike counts and the composition of those counts. Monthly bird strikes shows a little trend. The decomposition shows evidence of seasonality and trend. The trend also shows evidence of the impact of COVID-19, where the flights during the 2020s were reduced due to this epidemic. Finally, the noise is presented, which appears to be random. Presented on this slide are four interesting proportion charts. Starting on the upper left and going clockwise, the time of day is broken down by dawn, day, dusk, and night. Daytime appears to be most prevalent. For the phase of flight, majority of the strikes happen during approach, which is where the Jeju flight was when the incident happened. For size, while there is a downtrend of medium-sized wildlife strikes, there is an increasing trend of small-sized bird or wildlife strikes. Finally, nearly all strikes occur in dry weather, with fog and rain contributing marginally. Snow-related strikes are negligible. This is probably due to more wildlife fly when the weather is dry. Correlation was essentially used to select the predictors. This chart shows the correlation table. Size small with 0.33 shows strongest positive correlation with strike frequency, suggesting small wildlife is more frequently involved. Speed median with 0.21 may reflect operational changes during periods with more strikes, for example, takeoff, landing speeds. Sky no cloud with 0.15 indicates increased visibility and activity under clearer skies. This perhaps indicates that birds fly more frequently on clear days. Phase of flight descent at 0.12. Descent phase has a moderate link with strike occurrence. Precipitation, fog, and rain with 0.1 is associated with decreased visibility and potential bird disorientation. Time of day, night, with a negative 0.09 correlation shows a negative association. This is possibly due to reduced bird activity at night. Height median with 0.03 is included due to operational relevance despite the weak correlation. Time of day dawn with negative 0.09 is included to represent low light transition conditions, which may affect wildlife behavior. And finally, phase of flight, climb, with negative 0.12 shows an inverse relationship with strike counts. This is important to include due to aircraft vulnerability during climb. 4 forecasting models were implemented to predict monthly wildlife strike incidents. These are SARIMA, ARIMAX, SARIMAX, and Bayesian Structural Time Series, or BSTS. The SARIMA model captures temporal dependencies and seasonal patterns, but without the external inputs. It serves as a strong baseline. ARIMAX, on the other hand, incorporates exogenous variables such as wildlife size, flight phase, and weather, but excludes seasonal components. Finally, SARIMAX and BSTS combines both seasonality and external regressors, allowing for a more comprehensive representation of strike behavior. These charts show the forecast versus actual comparisons for the 4 models. ARIMAX shows almost flat predictions compared to the other models. SARIMA and SARIMAX models appears to be very close to each other with large standard deviations on its predictions, which is likely due to reflection of seasonality. Finally, the seasonality is very evident in the BSTS model. Now for the performance comparisons. The Bayesian Structural Time Series BSTS model emerges as the most effective choice for forecasting monthly wildlife strike incidents. It achieved the lowest RMSE of 8.95 of all models tested and provided an explanatory power of R squared equal to 0.67. Unlike traditional models, BSTS integrates local trends, seasonality, and multiple exogenous variables within a probabilistic framework, allowing for credible intervals that capture forecast uncertainty, which is critical in aviation, safety planning, and resource allocation. In comparison, SARIMA performed well due to its strong modeling of seasonal patterns, but its lack of covariate integration limits its adaptability to external influences such as weather or operational conditions. ARIMAX, despite incorporating external regressors, underperformed due to its omission of seasonal structure, which is clearly present in the data. SARIMAX offered a more balanced approach, combining the strength of SARIMA and ARIMAX. However, its marginal improvement in accuracy over SARIMA suggests diminishing returns relative to its increased complexity. Ultimately, BSTS provides the most flexible and informative forecasts, making it especially suitable for operational use in environments where decision makers must account for uncertainty and respond to changing conditions. It supports scenario planning and risk assessment more effectively than point estimate models. The monthly BSTS forecast shows clear seasonal patterns in predicted wildlife strikes. April shows the highest average strike risk, followed by a secondary peak in October and November, aligning with typical bird migration periods. February and March have the lowest predicted counts, indicating a relative lull in wildlife activity. Strike predictions are fairly consistent during the summer months, with moderate risk across May to July. Overall, the model shows low variability month to month, suggesting reliable seasonality and supporting targeted mitigation efforts during peak months. And this ends my final report. Thank you for your time. Bye.